1.2 is on the norm and the dot product. So let's take a look at that. So first, we're going to define the norm or the magnitude of a vector. So let v and w be vectors in Rn. So where we write it like that. And so in R2, it's the same thing we've done before, similar to Calc 3 or anything using vectors. You have some vector, you can assume that the initial point is the origin. The terminal point is like essentially a point in space or a plane. And then you can just use Pythagorean theorem to talk about the distance. So essentially that's how we're going to define the norm for a vector in Rn. So it's a similar connotation concept if you can visualize that. So we say, I like to use the two bars on the side. So the norm of v is equal to the square root of the sum of the squares of the components, v1 squared plus v2 squared, etc., all the way to v sub n squared. So that's the definition. And then theorem 1.2 gives us the properties. So this is the property of the norm of, or magnitude. So norm or magnitude of v in Rn. And so let's let little r be in the reals. 1, magnitude of or norm of v is greater than or equal to 0. And magnitude of v equals 0 if and only if v is 0. V is the 0 vector. Okay, that one's pretty straightforward. Kind of makes sense. 2, we can factor out the r in absolute values. We've seen this, did this exact thing in Calc 3. So you factor out the r, the constant, and you get absolute values. We'll prove that one. 3 is a triangle inequality. Prove this one as well. V plus w is less than or equal to magnitude v plus magnitude w. Okay, and that's referred to as the triangle inequality. So that essentially means that the sum of this distance has to be less than the sum of the other two's distance combined. So this plus this must be greater than that distance. That's essentially what it's saying. Okay, so let's look at the proof. Well, we won't do all three. We'll do, I think I do 2 of them. Let's see. So the first one, pretty straightforward. Let's let v be in Rn, and r a real number, constant, scalar. Magnitude Rv, by definition, is equal to magnitude Rv1, Rv2, etc. to Rvn. Now that's equal to, so that's actually just definition of scalar multiple, right? Scalar multiple. And then we're going to take the sum of these squared. By definition of magnitude, that's the square root of Rv1 squared plus etc. Rvn squared. But that r is the same for each term. So you can factor it out and get absolute values, or square root. So that's equal to the square root of, and then it ends up being r squared, and then v1 squared to vn squared. And then when you do the square root of r squared, that's absolute value. So v1 squared to vn squared. So that's absolute value of r, and then times its magnitude, or v magnitude. You're basically back to v magnitude there. Okay, I'll do the triangle inequality a little later, it looks like. Okay, so let's look at an example then. Let's let v equal 4, -1, 2, 3, -2. Okay, so that is in what? What's the dimension there? 1, 2, 3, 4, 5. That's an R5. And so let's just calculate magnitude of V. So this is just a kind of a warm-up type question. Okay, so then that's 4 squared plus 1 squared plus 2 squared plus 3 squared plus 2 squared. That ends up being 34, square root of 34. 16 plus 1 plus 4 plus 9 plus 4. Okay, unit vectors. So let's talk about that a little bit. I'm going to talk about unit vectors. So magnitude of u equal to 1. So u is called a unit vector. So if you take some vector v in Rn and you divide by its magnitude, then it becomes a unit vector. Okay, so that when you divide by its own magnitude, you get a unit vector. That's the concept. Okay. So let's look at an example. So find the unit vector in the direction of v equal to 1, -1, 2, 4. So you can see my examples, I'm trying to use something other than R2 and R3, because that's what we did in Calc 3. We used either R2 or R3. So now I want to extend stuff to higher dimensions to get used to looking at it like that. So to do that, pretty straightforward, right? You just do magnitude of V, which is equal to the square root of the sum of those squares, 1 squared plus 1 squared plus 2 squared plus 4 squared. Of course, I'm squaring the negative becomes positive. That's the square root of 22. Double check my math there, my arithmetic. So u, the unit vector, is v over its magnitude. So you divide by magnitude. So that's going to be 1 over root 22 times the 1, -1, 2, 4. So you can distribute that if you want. It becomes 1 over root 22, -1 over root 22, 2 over square root of 22, and 4 over the square root of 22. Just a quick note, if you look at the standard unit vectors, so E1 through En, so the standard unit vectors, standard basis vectors, so the standard basis vectors are all unit vectors. Right, does that make sense? I mean, if you take the magnitude of any of those, you're basically just doing the square root of a bunch of zeros and then 1 squared. So square root of 1 squared has to be 1. So pretty straightforward there, just like I, j, and k, right? Just like I, j, k. Those were all unit vectors as well. Okay, let's see where I'm at here. Let me go and cut this one short because I need to clean up a little bit, a couple things here. So we will go on to the dot product, the Cauchy-Schwarz inequality, and then I'll come back to proving the triangle inequality. So I want to make sure we're on point on everything else. So we'll probably do 3 videos for this section.